This tutorial session will be about neuromorphic sensors, and the first talk will be about neuromorphic vision sensors or silicon retinas. The talk will be given by Professor Tobi Delbruck, and the following talk after this will be on neuromorphic audition by Professor Shih-Chii Liu. Both of them have been pioneers in the field. So anybody who has followed the area of neuromorphic engineering would have heard of Professor Carver Mead. His lab in Caltech was where this research really started. And both Tobi and Shih-Chii were present in that lab and doing this early part of the research. So it so happens that my PhD advisor, Professor Jennifer Hassler, was also part of that lab and their colleague. So I can say that Tobi and Shih-Chii are in some sense my academic uncle and aunt. So let me start off with the first introduction about the first talk. This one, the title of the talk is Event Cameras from Biology to Circuits to Applications. Tobi has a pretty long biography, so I'll just maybe say some of the salient parts of his biography. He is, as I said, he graduated from Caltech in the inaugural class of the Computation and Neural Systems program founded by John Hopfield, and he was a student of Christof Koch, David Van Essen, and Carver Mead. Currently, he's a professor of physics and electrical engineering at ETH Zurich in the Institute of Neuroinformatics at University of Zurich and ETH Zurich. And he and Shih-Chii together direct the sensors group there, which focuses on neuromorphic event sensors and processing, with a recent shift in focus towards theory and hardware accelerators for AI. So one of the very big contributions that both Tobi and Shih-Chii have made is organizing the Telluride Neuromorphic Workshop, which is annually held in Colorado. Telluride is the oldest neuromorphic workshop, and which I also attended as a student. I think most of the people who are in neuromorphic community would like to potentially go and attend that to get a real good feel about how people work in this area. It's really amazing. Tobi has many wonderful inventions. I think his research has resulted in 3 startup companies: InniLabs, Insightness, and Innovation. He invented the neuromorphic adaptive photoreceptor circuit, and incidentally, part of that circuit is a pseudo resistor that is widely commercially used also in neural recording amplifiers. His papers have won more than 13 awards, and in 2013, he was named a fellow of IEEE Circuits and Systems Society for his work on neuromorphic sensors and processing. So, I mean, he likes a lot of hobbies, likes to read storybooks, play tennis, and sometimes does card tricks on unwary subjects. And I myself have been on the receiving end of one such card trick. So I think with that, let me pass the time over to Tobi, and you can see him with his pack of cards over there. Before we actually start the the recorded video, I would actually emphasize one thing. Tobi's and Shih-Chii both are one of the few persons whom I have seen are still very much hands-on in terms of technical work. So I would really encourage all the students to take this opportunity and ask any sort of circuit questions, algorithms questions, any detailed technical questions that you have. So you would be amazed by their knowledge and insight. Okay, so with that, let me not take any more time, but pass the time over to the actual tutorial session.
Hello, everybody. My name is Tobi Delbruck. I'm at the Sensors Group at the Institute of Neuroinformatics, University of Zurich and ETH Zurich, and this tutorial is about event cameras, cameras that mimic somehow, as seen as this video, the spiking output of the eye that puts out brightness changes and somehow mimics a very simplified functionality of the real retina. Now, this is a very long tutorial, so I don't expect anybody to watch it in one sitting. I recommend that you look at it piece by piece and look at the index that's in YouTube of the different slides. You can then jump around and random access this whole tutorial. This tutorial has 3 parts. The first part is about the history of silicon retinas, going all the way back to Misha Mahowald and Carver Mead's Silicon Sees a Cat. Then the bulk of the tutorial is about event camera technology. Here, this video from Davide Scaramuzza, which I'll show later again, contrasts a conventional camera that puts out full frames with the brightness change stream of events from a dynamic vision sensor, which constitutes the dominant technology for this kind of sensor. And the bulk of the tutorial is about the pixel technology itself. We invented these pixels a long time ago, and we've been working on it since then, and we understand a lot of the second order effects, and I've tried to put that into this tutorial. The third part of the tutorial is about algorithms and applications of event cameras in robotics and AI. And I recommend you also look at the lovely tutorial from Davide Scaramuzza, where he talks a lot more about computer vision algorithms. I'm kind of talking here about low-level representations of information and inference and building robots out of this kind of technology. Okay, so enjoy. So let's start about thinking about the human eye as a digital camera. In the eye, the light comes in through the cornea and then the lens. It gets focused on the sheet of retinal tissue at the back of the eye, which is about 1/3 of a millimeter thick. And it passes through the neural tissue for most of the eye, except for the photoreceptor. It passes through the tissue onto the photoreceptors, and then all the computation here is completely analog, biochemical and electrical, until it comes out as spikes on the optic nerve. But it starts here in the rod and cone photoreceptors, passes by the lateral network of horizontal cells, which do a kind of a spatial temporal averaging of the photoreceptor signals. And then it goes through the bipolar cells. We call bipolar because they have two kind of poles around the cell body. And then through a thick layer of amacrine cells, which is underrepresented here, does this complex spatiotemporal computations, and then finally comes out as spikes on the optic nerve, as I said before. Now, if we look at the specifications of the eye, it has 100 million photoreceptors in the human eye, only 1 million output fibers carrying up to at most 100 Hertz spike rates, incredible dynamic range of 180 dB or 10 to the 9 operating range from dark starlight, where you can barely see the horizon, night sky, up to bright sunlight. Actually, there are about 20 different eyes within the eye. As Botan Broshka has pointed out many times, there isn't just one or two classes of ganglion cells. There are at least 20 different classes of ganglion cells that compute different aspects of the visual input, which biologists are still trying to understand. So it's a complex beast, and it does a lot of computation, at least many teraops per second in the eye. And how much power does it burn? Well, people have estimated that the human eye burns about 3 milliwatts. Compare that with several hundred milliwatts for a state-of-the-art smartphone image sensor alone, without any computation. So it's really quite amazing specifications. But for the purpose of this presentation and tutorial on event cameras, the output is a sparse, asynchronous stream of digital spike events that represent dynamics of the input, in particular brightness changes at the input. And that represents a large class of ganglion cells, particularly in the peripheral retina, that only respond to transient signals. So let's look at the concise Tobi bias timeline of electronics, neuroscience, artificial intelligence, and neuromorphic engineering over history from 1945 up to 2015. Electronics started with the Colossus around World War II. At 2015, it was up to smartphone application processors with really considerable power. Neuroscience started with Hodgkin-Huxley neuron model back here and discovered only the grid cells in the navigational system about a decade ago. And then artificial intelligence started with McCulloch's pit neuron, and now it's gone up to AlphaGo, Atari games. The fact that smartphones now include accelerators for feed-forward convolutional neural networks, and neuromorphic engineering didn't start until the mid-1980s with Fukushima's neocognitron and the first application-specific silicon neurons and silicon retina from Hopfield and Mead and Carver's group at Caltech. It wasn't until about 1988 or so, 89. That's not true. About 1990, late 1980s, that the first address event representation protocol was defined in Carver's group at Caltech, allowed neuromorphic chips to send out spike events instead of frames of data. And that's led now to the developments you can ponder later. We came up with our first DVS silicon retina around 2006. That was the first silicon retina that provided usable performance for real applications. That's led now to the establishment of several startups. And in the last 3 or 4 years, the production of these dynamic vision sensors from major semiconductor providers, Samsung and Sony, on their state-of-the-art image sensor production lines. So now, if we look at the historical development of neuromorphic engineering, you can look at a recent article from Carver, a short article from Carver in Nature Electronics, how we created neuromorphic engineering. I'll leave that for you to look for yourself. But here you can see Carver and Misha in the physics of computation lab at Caltech, and during the development of these kind of neuromorphic chips from the early days. Just to put this, so let's look at the Misha Mahold Carver Mead retina that made the cover of Scientific American. This is a very interesting structure, which has a photoreceptor, which drives a transconductance amplifier, which drives a node of a 2D resistive network. And then inside the pixel, you take a difference between the resistive network and the photoreceptor. And this diagram shows the resistive network. A single pixel element is illustrated in the circular window. The silicon model of the triad synapse consists of a follower-connected transconductance amplifier by which the photoreceptor drives the resistive network through this transverse conductance and to the lateral conductance, and an amplifier, a transconductance amplifier that takes the difference here. And the pixels are tiled in a hexagonal grid. And so the operation of this pixel, which models Koeffler's 3-layer retina, is that the logarithmic photoreceptor now has its spatiotemporal average computed by this resistive network. So the resistive network expresses a kind of a low-pass filtered version of the visual input, and then the output of the retina is the difference between the local value and the low-pass value. So it's kind of a high-pass filter, spatiotemporal high-pass filter. And you can see that in an output where Misha shot a picture of herself. This is a Polaroid photo made from the multi-sync monitor screen. And Misha was just slowly moving her head back and forth here. And you can see now that wherever the intensity is kind of uniform, it goes to a uniform gray level. That's because any place the intensity is uniform, the average value computed by the resistive network takes on the same value as the photoreceptor, and there's no difference, and then there's no net output current. But if a particular feature is darker than the average or brighter than the average, then the difference is expressed by the voltage difference, and that drives out either a negative current or a positive current, which gets turned into video brightness. So that's the idea of this thing. It does a kind of a cool operation. Obviously, it's quite expensive. If you look at the actual pixel circuit, you know, you'll have about 20 transistors over here. And you can see in these days we used mistakenly a bipolar transistor, thinking that this current gain here was beneficial. Actually, it's not, for reasons I won't go into here. But basically, this is the same photoreceptor feedback arrangement that we use in the DVS. You know, you have an inverting amplifier here. You have logarithmic feedback through the subthreshold transistor. In this case, it's a continuous time high pass. You see the feedback is through this capacitor divider, but then the DC level is set through this early pseudo resistor. We don't use this structure anymore, but it was kind of a pseudo resistor, which would set the DC level. So the DC gain was just set to a low level, and then it would result in a high AC gain. And what about these resistors here? Actually, those are not resistors. Those are MOS transistors. And I encourage you to go look and read in the Analog VLSI and Neural Systems book about Carver Mead's HRES circuit. It used a transconductance amplifier with an additional transistor in one branch that would voltage shift, and then it would bias the MOS transistors in a particular arrangement to make these 6 resistive connections to the neighbors in a pretty efficient way. But still, it's a lot of transistors here to do this rather simple spatial temporal averaging and high-pass filtering operation. But the really big problem with this thing, with this circuit, is you can see in the output, if I zoom up right here in this area and look at this area over here, it should be uniform, right? Because just the white wall back there. But actually, if you look at it, you'll see tons of pixel-to-pixel mismatch. fixed pattern noise. And the problem is that dopant fluctuation in the transistors channels results in threshold variation, which results in huge differences on the order of many tens of percent in the DC current flowing through the transistor at any particular operating voltage. And so basically it meant that unless you had a very high contrast stimulus, you just couldn't get any output. The signal was just buried in the salt and pepper noise. That's coupled with the low fill factor and the fact that it didn't really do a lot of operations that were that useful, kind of doomed this design. In context here, I'll show you one example of a chip that I worked on over the period 1985 to 96. I think this is about 1991. It's the so-called time derivative adaptive silicon photoreceptor array that was published in an SPIE meeting around that time. Let's look at the pixel here. So basically we had in this pixel, each pixel had one of our adaptive photoreceptor circuits. It had a photodiode. It's very much like the DVS front end, except it was higher gain. I had a photodiode, a subthreshold transistor providing the logarithmic response here, and then the feedback was around an inverting amplifier and an RC network with a pseudo resistor. This transistor acts like a very high resistance pseudo resistor. And then this thing had more gain because of this cap divider ratio. So this is about 1 to 10 capacitor here. And that amplified the transient changes much more than the DC changes. Now in this particular scanned silicon retina pixel, there's no spiking output. It would just scan out frame by frame. The cool thing about it is that this pixel photoreceptor signal was coupled to a kind of a source follower readout, much like is used in current active pixel sensor CMOS image sensors. You can see the signal here is coupled so that when you select this particular row, the voltage signal that is currently capacitively coupled to this point is read out on a column current readout. So we actually had current readout on this thing, not voltage readout. But then at the same time, when the next row is selected, which selects its column readout, it actually resets this row by tying this node here to a reset voltage. So in each frame of readout, you basically would read out the difference from the previous frame. And you can see that here in this video output. This is showing Kwabena Boahen, who was at that time a Ph.D. student in Carver's lab. And you can see how now it just responds to the changes in his input. At that time, the pixels were huge. I think they were about 60 microns on a side, and we had about maybe 32 pixels on a side. So that was the early days of silicon retina development. Okay, we'll now go into the second part of the tutorial, which is dynamic vision sensor event camera technology. Now let's take a step back and compare conventional cameras, or so-called static vision sensors, which output a stroboscopic sequence of frames. So let's look at the state of the art there. So basically this is an idea which has been around now for 150 years. You can see here the famous movie, the very first 40-frame movie shot by Muybridge in 1878. That's 150 years ago now, which established for his sponsor, Leland Stanford, the fact that all 4 feet were off the ground at the same time. Incidentally, if you're not familiar with Muybridge, I highly recommend looking at this article here about Muybridge, especially the O.J. Simpson equivalent murder of the century trial, which involves Stanford, the same Stanford, the California industrialist who founded Stanford University. It's a very interesting story, and it'll help you remember Muybridge. The point here is that this idea of a sequence of frames being the foundation of computer vision is now very old, 150 years. That means it was a good idea. And it is good because this idea is compatible with more than 50 years of machine vision. It allows you to make sensors with small pixels, like 1 micron for consumer electronics, even sub-micron, and maybe 2 to 4 microns nowadays for machine vision sensors with global shutter and higher SNR and stuff like that. But it's also bad because you produce a very redundant output. These pixels just say the same thing over and over again. Of course, you have temporal aliasing. If anything moves faster than the Nyquist frequency of whatever frame rate you globally choose, you get aliasing. And because everybody shares the same integration time, you have limited dynamic range, unless you do some special tricks. You have limited dynamic range, about 60 dB, factor of 1,000, say from 1 millivolt to 1 volt, which you can represent. But the real world is much higher dynamic range than that. I mean, it goes up to over 100 dB, 120 dB when you have extreme shadows in the scene. And you have this fundamental problem that the average latency to respond to the input is half the frame interval. So fundamentally, you have this problem of latency versus power. In other words, you can get the latency as short as you like, but to do that, you have to burn more power, right, to go to a higher frame rate and to process those higher frame rate. Or you can burn very, very low power by going at very low frame rate, but of course, then the latency, gets long. So that's the fundamental trade-off you have to face. So these considerations led us to the invention of the dynamic vision sensor, or DVS Pixel. And it's described here in this JSSC paper. But basically, let's think about it like a cross-section of the retina here. Here we have the photoreceptors, the bipolar cells, and the horizontal cells. If you look at the components of this DVS Pixel, it starts with a photoreceptor. It's driven by a photodiode, which then goes into a 3 or 4 transistor logarithmic photoreceptor circuit. This runs in continuous time. And then that's capacitively coupled to a change amplifier that kind of mimics the bipolar cells here. This change amplifier is reset by closing the switch and then opening it every time the pixel sends out an event. And this change amplifier now amplifies the change in log intensity by some factor, maybe about 20. And then that is driven into 2 comparators, which mimic the ganglion cells here, that detect on and off brightness changes. So when this change amplifier is reset, its output sits here. And then these comparators detect whether the signal went up past an on threshold, this one here, or down past an off threshold here. And so as a result, inside the pixel, you get these on or off brightness change events that can happen at any time asynchronously. So there's no clock here. And then when the pixel outputs this on or off brightness change event, which represents a plus or minus delta log I, where delta is this threshold here of log intensity change, when the pixel outputs this on or off event, which results in the address of that pixel being sent off along with the sign of the brightness change, then that results in resetting the pixel and memorizing the new log intensity. So that is the basic operation of the pixel. Now, if we look at this beautiful video from Davide Scaramuzza at the Robotics and Perception Group at the university, compares an event camera with a frame camera. As you can see here, a standard camera, when it sees a black rotating dot like this, produces a sequence of frames that are quite redundant. Most of the pixels don't change, and the location is aliased. By contrast, a dynamic vision sensor outputs a stream of brightness change events that only tell you about the moving dot. When the dot stops moving, standard camera keeps putting out the same frame over and over again. DVS just doesn't put anything out at all. If the dot starts moving really, really fast, standard camera aliases terribly if it's undersampled, and it also blurs the images. And an ideal DVS just reports a tighter helix in space-time of these brightness change events. Okay, this slide shows that the DVS pixel has a wide dynamic range because of its architecture. In this scene, we took an image density step chart and exposed it to a very high contrast shadow, or 780 lux on the bright part and 5.8 lux falling in the dark part. And this image density step chart has about 0.1 density step, about 25% contrast between each of these little squares. And so what you can see with that is that the standard camera can either expose for the dark part of the scene or for the bright part of the scene, but it can expose for both parts. Now on the left side here, we show the DVS output. Where it's gray here means there were no spike events. Where it's white, it means there were on events generated. And where it's darker than gray, it means off events were generated. And there is a shadow line here going across the scene, but the shadow line is not moving. The only thing that's moving is its density step chart. And you can see in the video here that the DBS can respond to both sides of this very high dynamic range scene. It can see this high contrast text, and it can even, and some of the pixels, or most of them, can even respond across both sides of the shadow line to these lower contrast steps. So that's one very nice characteristic of this kind of sensor, is that it is useful over wide dynamic range scenes. The other nice characteristic for a DVS event camera is that it has a sparse and quick output. Now in this video I'm going to play here, the data rate is always less than a megabyte per second, but it has an equivalent frame rate of a 10 kilohertz camera, but 100 times less data. So this video here shows two coins recorded with a 346 by 260 pixel Davis DVS camera, and it shows two coins here spinning. And you can see here, because of the event output, we can slow down this normal scene by a factor of 30 or 40, I think, to catch the collision of the two coins. So if you are a computer vision person, the only pixels you need to process are the ones that are producing these brightness change events, and you get these brightness change events within a millisecond or so of it happening out in the world. It makes it quite easy to do some high-speed vision problems very cheaply. In our latest sensors, we call Davis, which stands for Dynamic and Active Pixel Vision Sensor. We take the DVS pixel that I showed you before, and we strap on another 3 or 4 transistor circuit here, consisting of a capacitor, to integrate the photocurrent, which flows through this logarithmic photoreceptor. So we continuously sense the log intensity here, but then the same photocurrent is not copied, it just flows through the circuit, and we now integrate it onto a capacitor. At the beginning of the frame, we reset the capacitor to a high voltage, and then it goes down like this, and then the output here, we read out the intensity at the end of that integration time. So by taking the difference of those two values, we get a differentially double sampled measure of the absolute intensity. It doesn't make for a great image sensor, but it gives us a static output stream as well as a dynamic output stream. If you look at one of these event cameras chip, and here's an example of a Davis 346, typically it has the pixel array here. This is a 180 nanometer CMOS image sensor process technology with a 346 by 260 pixel array, where every pixel is 18.5 microns. And if you look at this pixel array, it's then surrounded by the address of event representation DVS asynchronous event readout circuits on these two edges. I'll say more about these later, but these are basically arbiters that read out the asynchronous events from the pixel array. On the other two edges of the chip, you have the active pixel sensor column parallel A to D converters and a scanner. And then a very important component of all these event cameras is the so-called programmable bias generator. It's something that generates the thresholds, the bandwidth, the refractory period, and it's important that it generated over 7 decades of dynamic range, because the range of currents that you have inside a pixel like this is huge. And so you can read about that in this paper down here from Minhao Yang and me, addressable current reference array with 170 dB dynamic range. This is our latest generation so-called programmable bias generator that uses Bolton-Gielen current splitters to generate these digitally programmable bias currents. Let's look at a state-of-the-art version of the sensor. So here's an example from 2019 ISSCC from Samsung DVS Generation 4 camera. It's really not that much difference. You have a much larger pixel array, which is much smaller pixels, only 5 micron now, but it's still surrounded by the same digital readouts for the pixel contents, but it does integrate much more functionality. For example, a mobile industry processor interface output and much more logic that allows a sensor like this to do noise filtering and signal processing on the chip. But the pixel array is same thing here. Yeah, this is I'll say more about this later, but this is a stacked image sensor technology where the top wafer die does the photo diode and NMOS circuit, and the bottom one has all the digital and some of the other analog transistors. But the basic idea is the same. Pixel array surrounded by processing circuits. Okay, here you can see a close-up of the pixels from this ISSC. Well, actually, it's from the CVPR workshop on event-based vision. from 2019. Yeah, it's really amazing how the pixel has shrunk from the early days. I'll say more about that later too. Okay, so what does a typical event camera's output look like? Well, here you have a recording of Christian Brandley catching a football. At the same time, this is from a Davis camera, so we're getting the frames out about 2013. We're getting the frames at the same time the events are coming out as these red and green. And you can see how the events are coming out kind of ahead of the frames, and you can hear this pixel as the football passes through it. The pixels are emitting these spike events. Here's a recording of a tennis player hitting backhands, and in this case the frame rate of the gray frames is only about 6 Hertz, but the data rate is about 300 times higher than the DVS event data rate. Here you can see the foyer of the hotel in Capocaccia where we have our neuromorphic workshop. You can see some people walking around here. This plot down here shows the data rate coming out of the DVS stream. It's only about 25 kilo events per second. So it's microcontroller processing. And using rather simple digital algorithms that are microcontroller scale, you can follow these people and track them around. This data here shows some driving data from a Davis again. The spike events are shown as red and green when they're put out. And now in this video, we switch to grayscale in a moment. So the spike events are rendered as black and white, but we turn the frames on and off. So here is driving down the shore in Alghero. Here the frames are on, they're off. Now the frames go on, now they turn off. You can see here that it really makes no difference. You don't need these grayscale frames to see what's going on. So basically it suggests that you can do most vision problems as long as the camera is moving or the object is moving. You can do most vision problems without having this, this gray level output. And nowadays these cameras include inertial measurement unit. We were the first ones to put this IMU on there. But this IMU now allows you to do event by event derotation of the camera, Steadicam. And it shows here how even a rapidly vibrating camera can be stabilized by using the information from the inertial measurement unit to remove the motion of the camera, or actually just the camera rotation. So I hope this is helpful to explain something about the nature of this DVS output. But I'll go on now. I want to talk about DVS sensor specifications. So it's important to realize that these sensor specifications are different than traditional cameras. You know, you have the functionality. I'll just go through some of these items ranging over pixel size and process down to FPN and matching. So typically, authors of JSCC papers will report power consumption. Usually it's on the scale of tens of milliwatts for the entire chip. But it's important to realize that this is only at the die level. Typical actual camera will burn more like 500 milliwatts or a watt because it's completely dominated by the digital interface to the rest of the system. Also, authors always report dynamic range, 120 dB, for example, from 2 lux to 100 kilolux scene illumination with this particular lens. But you have to read the test conditions carefully to understand what's going on. And authors of solid-state circuits papers report response latency. In other words, we reported a minimum response latency for the DBS pixels of 15 microseconds at 1 kilolux chip illumination, and a maximum output bandwidth of 1 million events per second. And the computer vision community took that on and started saying in many of their papers that the sensors have microsecond response latency. It's not true. It's true in laboratory conditions, as a report in such a solid-state circuit paper, but it's not true in reality. These are artificial conditions. So in the real world, the latency of the pixel response is closer to 100 microseconds up to 10 milliseconds at low light intensity. I'll say more about that later too. And finally, people report fixed pattern noise. In CMOS image sensors, you typically report the pixel response non-uniformity. Here we report the fixed pattern noise as the uniformity of the temporal contrast threshold, the threshold to make a log intensity change event. And I'll say more about that later too. Okay, I want to say something about two key functional aspects of DVS pixels. Number one is mismatch reduction. If you look at the simplified view of the pixel again, starting with the photoreceptor capacitively coupled to a changed amplifier, which is then coupled to these comparators on the right here. The first thing you have to realize is that these are built out of CMOS transistors, and so these comparators are going to have random variation in their threshold, along with this amplifier here. The amplifier gain is well controlled by capacitor ratio. It's actually a switch cap amplifier, but you're going to have inevitable mismatch, random variation in the comparator threshold. For example, plus or minus 20 millivolts of mismatch here. The beautiful thing about this pixel is because of the amplifier and the gain going through this thing, this factor of about 10 or 20 of gain here, the mismatch referred to the input is reduced by the factor of this gain here. And so that turns a big mismatch over here of 20 millivolts, plus or minus 20 millivolts, into a plus or minus 2 millivolt or 1 millivolt mismatch here at the input referred. And that means that the mismatch at the input is 1 or 2 millivolts, which corresponds to just a few percent of contrast if you go through this log photoreceptor. So that's the number one thing probably that made this pixel usable with real world contrast. The second important aspect of this pixel is the bandwidth enhancement provided by this logarithmic active photoreceptor front end. You can see here how the feedback through this MFV of the photocurrent is coming back through this single stage cascoded inverting amplifier with this bias current IPR. So this feedback loop here increases this MFB source conductance by a factor of the loop gain, thus reducing the parasitic RC time constant that's associated with this photodiode. So think about it like this. If this voltage goes down 1 millivolt here at VD, normally, without this feedback loop, you would just have the source conductance of this MFB, which would be, the source conductance here would be proportional to the photocurrent. The conductance would be I over UT, the thermal voltage. But now when this goes down 1 millivolt, the output of the amplifier goes up 100 millivolts, if the gain is 100 here. So instead of the source going down 1 millivolt, now the gate goes up 100 millivolt. That increases the effective source conductance here, and that source conductance coupled with the parasitic parasitic capacitance of this photodiode determines the dominant pole of the response time. So the result is that this pixel is much faster than a passive pixel, and that lets it allow quickly, but with more noise, of course, to low light intensity. Okay. It's important to realize as a user of this pixel that all these operation of the pixel is affected by the bias currents. So you have really, I think, about 5 or 6 critical bias currents in a pixel like this. You have the photoreceptor bias current, you have the source follower bias current. These two together affect the bandwidth of the front end. So you can reduce the bandwidth to reduce noise or increase the bandwidth if you want to get quicker response. Then these 3 bias currents here, this ID, this I on and I off, determine the event threshold. Okay, so I'm going a bit fast here, but this shows the response of the pixel over time. As a function of time here, the voltage VD here, in this example, increases and then decreases. And that results in the output of this change detector here, VD, that's this signal right here, to respond to these intensity changes away from the reset level. And so if the intensity is increasing here, you get an on event, on, and then as it starts to decrease, you get off. And then when this comparator here crosses the on or off threshold, it generates an event. But these threshold levels are set by the relative currents between ID, I on, and I off, if you look through that. And the last bias that matters here is the refractory period. This circuit over here is the one that takes the row and column acknowledge signals, ANDs them together, and generates a low-going pulse here at reset. And this reset pulse then goes back into this switch here and shorts out the switch capacitor amplifier in the change detector. And this low-going pulse lasts for a certain amount of time after the row and column knowledge signals go away. It lasts for an amount of time here that's set by this refractory bias current. And you can see how this refractory period pulse here affects how long the pixel is so-called refractory, how long it ignores log intensity changes after it sends out an event. All right, so let's look at a measurement. So let's look in particular at an event threshold matching measurement. The experiment here is to apply a slow triangle wave LED stimulus to the entire array and measure the number of events that pixels generate. So here is the relative intensity of this LED stimulation as a function of time in seconds. It goes up and down and back up and down. And every time it goes up and down here, you get on and off events. You could measure the number of events that a pixel generates. It should generate on events here and off events here and so on. And now you can plot a distribution of the number of events per cycle across pixels here. So most pixels here generated about 11 events. Some generated less events because randomly the threshold was higher, and some generated more events because the threshold was lower. So this distribution here tells you the threshold matching, how well the thresholds are matched across pixels. We can see the mean here is about 11 events per cycle for a contrast of 3:1 in intensity. So the conclusion from this measurement is that pixels generate 11 plus or minus 3 events per factor of 3.3 in contrast. Since the natural log of 3.3 is 1.19, and 1.19 divided by 11 events is 0.11, we can conclude from this, in this experiment, that the contrast threshold is about 11% plus or minus 4%. And so that's how you measure in a DVS pixel the matching or the fixed pattern noise in the contrast threshold. I'll show you another measurement here of recent matching results from this Prophecy Sony paper of ISCAS 2020. They introduced a useful metrics called NCT and CDP for figures of merit. So in particular, they defined the nominal contrast threshold as the contrast with a probability of 0.5 of the pixels responding at 10 lux sensor illumination, not seen, sensor illumination. And in this particular measurement, they showed that the nominal contrast threshold that they could achieve was about 16% intensity change. At 16% intensity change, half the pixels actually responded to this log intensity change. And they also report a metric called contrast detection probability. This is a curve for contrast C. It's the value of S curves, for example, at 40% contrast. You see here, as a function of illuminance, log illuminance here, the pixel response probability goes up at this contrast setting. So they set the contrast threshold to 40%, not 15% like here. They set the contrast threshold to 40%, and now they change the absolute intensity, and they see over most intensity range, the contrast detection probability is almost 100%, right? So all the pixels. But then now as it gets darker and darker, because of the effect of dark current and bandwidth limitation, pixels stop responding, right? And down at about this intensity, which is quite low here, which we call the lower limit contrast, at this intensity here, only 50% of the pixels respond. And then as you make it darker and darker, the pixels just don't respond at all. Okay, so that's a nice useful metric to measure performance of these sensors. All right, let's look at one more metric of performance here, which is latency and jitter. So the DVS pixel latency is a result of finite transduction and conversion bandwidth. And computer vision papers about event cameras have made misleading claims, such as event cameras have no motion blur and have latency on the order of microseconds. This is from our recent paper on V2E, from video frames to realistic DVS event camera streams. So in this experiment here, we actually measured this latency. This is from our JSSC paper of 2008. Here we take an LED, we turn it off, and we see how long it takes for the DVS events to come out. And you can see here, most pixels respond with some nominal time, but there's some jitter in that timing. And we define this as the average latency. And this latency is a function of the illuminance. So you can see here the latency when we use nominal biases, that's like typical user biases here, are a soft function of absolute intensity. They go from about 4 milliseconds at a few lux chip illumination up to down to about 900 microseconds, or just less than a millisecond, with very bright chip illumination. Now, if we really crank up the pixel, turn up the photoreceptor and source follower biases, we can get the pixel to respond much quicker. You can see here we get a minimum latency about 15 microsecond. But you see now it's much stronger function of intensity, right? And it's very important to realize as a user that this is chip illumination. Once you go through the lens and optics and refer that back to scene illumination, you can see that this represents sunny day, this represents office illumination conditions, and this is a night street. So under home illumination conditions like your living room at night, you can expect latency, pixel latencies on the order of a few milliseconds from a DBS pixel, not sub-microsecond. It's still quick, but it's not like super duper quick. Okay. You can understand what's going on here if you do a detailed pixel simulation. So this simulation is from our V2E paper, shows the DBS pixel under low lighting conditions. You can see here the pixel is responding to a pattern which is moving by. So first, the pixel sees a bright scene, is a certain contrast bright scene, and then the scene gets dark. Okay, but it's like looking at railroad ties. You're in the sun, and all of a sudden you go into the tunnel. All right. Now this green curve here shows as a function of time here the photoreceptor response. Actually, this shows the photocurrent. You see when it's bright here, the photocurrent varies from 10 to about 20. It goes up and down. And then when it's dark, it varies from about 2 to 4. Of course, this photocurrent is sitting on top of a substantial dark current in the pixel. The green curve, the red curve here shows the photoreceptor response, this logarithmic photoreceptor voltage. You can see that it's low pass filtered compared to the photocurrent itself. Now, as this finite aperture pixel passes over this edge here, of course, the finite aperture results in some finite time that the photocurrent changes. But on top of that, the pixel also low pass filters the photocurrent just because of its own photoreceptor dynamics. And when it gets dark here, because of the way the logarithmic photoreceptor works, and the feedback conductance here is proportional to the photocurrent, the photoreceptor gets slow. Here, in this extreme example, the photoreceptor gets so slow that it can't even respond to these square wave input photocurrents. And as a result of that, the peak-to-peak variation of the photoreceptor output voltage gets smaller and smaller. And so as a result of that, instead of getting out this stream of on and off spike events, you get fewer spike events in this dark part of the scene, just because the voltage has been low pass filtered by the photoreceptor so that it doesn't change as much and it produces less events. But you can see the motion blur here too. As this edge passes over here, it takes finite time for the photoreceptor to respond, and that results in a burst of events that take finite time to come out of the pixel. I mean, ideally, you would want a burst of on or off events that's instantaneous. Like instantaneously, you should get like 3 or 4 events. But of course, nothing is instantaneous in the real world. So you actually get the equivalent of motion blur here, which result of finite photoreceptor dynamics. A key part of this DVS pixel is a 7-transistor 2-capacitor change detector, which consists of these 2 transistors here, P-FET and FET. These 2 here is the on comparator, these 2 here, the off comparator, and this feedback capacitor, and this input capacitor, and this reset switch. So, this circuit here amplifies the change in the log intensity from the log photoreceptor. The way it works is when you reset it, you close this switch, and that basically diode connects MDP. Diode connects it so that MDP sources this ID current. So this voltage here ends up near VDD, right? So that this transistor here has the current ID flowing through it. At the same time, I on is bigger than ID and I off is less than ID. So in this reset condition, since I on is bigger, I on, so this voltage here V on or on is low, and I off is less than ID, so this voltage here is high. Okay, so now you open the switch, disconnect it, and now if there's an increase of voltage here through C1, then the feedback, negative feedback through this amplifier, right? This goes down to increase the current, this goes up. This negative feedback now has to move VD so that VD, delta VD times C2 equals delta Vin times C1. You can see the voltage gain here is C1 over C2, negative C1 over C2. Just a very lovely, simple circuit. There's more we could say about this. For example, there is a junction leakage here from the VDD of this PFET to this node through this diode leakage current diode that causes on events, and because it always leaks a little bit of charge from VDD onto this node, so it makes it look like the intensity is slowly increasing. That results in this background leak events at typically about 0.1 hertz that increase with temperature and also increase with light intensity through parasitic photocurrent. So you want to make sure this thing is covered with metal so that light doesn't fall directly on this parasitic photodiode. But that's a parasitic effect. But the main beautiful thing about this circuit that is so lovely is that it turns out that it results in temperature-independent contrast threshold, as I'll now demonstrate. So think about just this transistors here. So together with the log photoreceptor, it provides temperature-independent temporal contrast threshold. So look at the circuit again here. It turns out that if these subthreshold bias currents have constant ratio to each other, which is easy to do if you use a Bolton-Geelan current splitter to derive ID, I on, and I off from some master current, then the temporal contrast threshold will be temperature independent. And the reason for that is actually quite easy to see. We know that the photoreceptor output voltage here proportional to the thermal voltage. This is UT is the thermal voltage, KT over Q, times the natural log of I. That's a result of this feedback transistor characteristic here. So this voltage here is proportional to absolute temperature. In other words, the gain is proportional to absolute temperature. Well, it turns out that the threshold voltage, for example, of this on comparator here through this amplifier, is also proportional, is inversely proportional to absolute temperature. If you work it out, as proportional to the natural log of I on over ID, the ratio of these two currents. So this UT and this 1 over UT cancel out. And so the temporal contrast threshold, theta on, which is the threshold in delta log intensity, let's say it's around 0.25 delta log intensity, is proportional to the natural log of the ratio of these two currents. There's no temperature in there, which is quite cool. Means you don't have to adjust the biases with temperature. You get the same behavior independent of temperature. So you can see this temperature independence behavior in a Davis 240 response in a video that's recorded at 0.7 degrees centigrade, 25 degrees centigrade, at 81 degrees centigrade, as shown here. If I play this video, you'll see that the response is, by the way, it has the frames coming out here, and the events here are rendered as red for off and green for on. You can see the response here is basically largely independent of temperature. It's hard to tell what the temperature is. The only thing you can see perhaps is at the highest temperature, 81 degrees, you can see more background activity, more leak event activity. But basically the response doesn't change hardly with temperature at all, and that's demonstrated in these curves that are reported in this paper, Transaction Electron Devices paper, which shows the temporal contrast threshold in delta log intensity per event. So it's around 0.3 delta log intensity, delta log intensity, so that's around contrast threshold around 25%. It's independent of temperature over this large temperature range from 0 to 60 degrees. And it does go up as the temperature gets really high for off events because of the increased leak current through this junction leakage diode. Yeah, but it's quite a cool effect. It means you don't have to worry too much about controlling the biases with temperature. So over the last 20 or 30 years now, there's been a remarkable reduction in pixel size. You don't see it, but back around 1980, 1985, the pixels were up around 60, 80 microns in these 2 or 3 micron technology that we were using then. But this is a plot of some data that I've collected over the years of the DVS pixel size as a function of year. Around the publication of the first DVS, we were using 350 nanometer technology, a pixel size of 40 microns. Since we went to 180 nanometer, the pixel size went down to 30 micron. Again, another pixel shrink down to 18 micron. And I think it was in 2016, Samsung reported in 90 nanometer technology a 9 micron pixel. And just last year, both Sony and Samsung reported stacked image sensor DVS with 5 micron pixel. That still has to be compared with global shutter automotive APS around 2 to 4 micron and rolling shutter consumer active pixel sensors around, now I think the minimum report is about 0.8 micron. But now the DVS pixels are getting so they actually look economical, which was one of the major problems with this sensor technology, that the pixels were just too big. In terms of dimension, DVS pixel is about 150 times the tech node historically, compared with 40 times the tech node for rolling shutter APS. So that's a good metric of where you might be able to go. Just really remarkable, the effect of stacked image sensor technologies pioneered by Sony. In this paper from 2020 ISSCC, Prophecy Sony, they reported a stacked image sensor technology pixel, a DVS, where the top layer has a photodiode and NMOS, and the bottom layer has all the other stuff. It's 90 nanometer back illuminated CMOS image sensor technology and 40 nanometer CMOS digital or mixed signal technology. They achieve a 4.86 micron pitch and is more than 77% fill factor. And you can see the stacking technology uses a copper-copper connection just from the photoreceptor. You see they put the NFET, the PFET on the bottom thing. So they make a copper connection right at this point in the photoreceptor, right? And so they do a pixel-pixel copper-copper connection with photodiode plus NMOS on the top CMOS image sensor and all other pixel circuit, which is about 50 transistors worth on the bottom CMOS. There have been some advances in DVS Pixel Circuit reported in the last few years in ISSCC and CVPR workshops. One example of this is the Cellepixel design as reported at CVPR workshops on event-based vision in 2019. You see it shares the same logarithmic photoreceptor front end. There's an undisclosed filter amplifier, which is followed by some kind of on-off comparator with some logic gates and the usual memory handshaking logic. And the distinctive feature about the Cellepixel design is that it offers kind of a random access logarithmic readout. So as soon as the pixel makes an event here, they can select that pixel and multiplex out the analog logarithmic voltage through this source follower readout. Of course, this has problems of the mismatch, pixel to pixel mismatch of that means that each sensor needs to be calibrated at the pixel level, presumably with some kind of a gray screen which is stored where the offsets are stored in firmware or something, or possibly it's some kind of a very long time constant high pass filter. But in general, it basically looks almost like a DVS pixel. They claim it's not verbally to me, but they never disclose the actual circuit, so it's not clear. Another example of a recent design that was published in ISSCC is the Prophecy Sony paper from ISSC 2020. Again, they have a logarithmic front end followed by an asynchronous delta modulator, basically this circuit here, followed by this undisclosed comparator and some logic. Again, they don't really disclose what the circuits are, so it's hard to say what's going on there. It's possible they may not disclose this stuff here and here because they fall short in disclosing the pixel circuit, possibly to avoid disclosing they use IP that they haven't licensed in these spin-off companies. Now, one paper that did disclose some interesting thing is the Samsung paper from ISSCC 2017. I won't go through all the details of this pixel, but you see that actually to supply the pixel at the transistor level, at least up to the point that they show the handshaking logic. And this sensor featured the group readout scheme. And the cool things about this pixel are that incorporated a self-cascode and feedback gain generation here, which increases the gain, which allows smaller C1 over C2 ratio and thus smaller pixel area. And you can see how that works. If you look at the pixel here, instead of having just this inverting amplifier with this logarithmic feedback transistor that's operated in common source mode here, it's an NFET here, right? So what they do is they put an MN2 which cascodes MN1. That increases the voltage gain looking down this way. That increases the voltage gain of this amplifier, which increases the total loop gain, which increases the effective source conductance looking back up this way, right? And the higher the gain of this amplifier here, when you pull this down, if this gain is higher, it makes this gate swing more, which makes it looks like the source conductance is higher here, which speeds up the pixel because it reduces the pole here at the front end. Basically, higher conductance here coupled with capacitance here decreases the time constant and makes the pixel go faster if you want it to. Of course, you can always low-pass filter it by reducing this supply current here in this point and also in the source follower if you want to limit the bandwidth for limiting noise. The other cool thing is about the gain generation. Because there are now two NFETs going back, the gain going back from the output to the input is reduced. When you reduce the gain going back, you increase the output gain, because the whole point of this feedback here is to hold the photodiode voltage fixed, clamped at a virtual ground. So if you decrease the gain by degenerating it through these two transistors here, you increase the output voltage. And this increased output voltage increases the voltage gain, which means that you can make these capacitors smaller here for the same threshold temporal contrast. At the same time, this increased voltage gain at the front end, together with this limited supply voltage, decreases the overall dynamic range from about 120 dB to about 90 dB. That's usually fine for most applications, but it does mean that the pixel can saturate under extremely bright illumination. Now, the other cool thing they did in this pixel design was this little trick that we actually tried in a prototype silicon long time before, but we never published it. But here they actually tie the output of this feedback amplifier in this differentiator. They tie the bulk of this feedback PFET to the output. And tying the bulk of the PFET switch to the output reduces the parasitic leak current from the bulk here of this PFET to this floating node. And the effect of that is quite dramatic. I've seen it myself, that it reduces the leakage current from VDD, which normally this N well is sitting in. This PFET is normally sitting in N well, so normally there's a junction leakage current from the N well to here, basically a current flowing onto this node from VDD, which creates these parasitic on leak events. In effect, this leakage current, which increases the temperature because all junction current increases every 8 degrees, it doubles. If you reduce that leakage current, then you reduce the effect of this virtual increase of light intensity. Like putting charge onto this node is like increasing the light intensity. And so when you do that, when you tie the bulk back to the source or drain of this PFET here, it reduces this leakage current a lot. Of course, it does mean that in one direction, when Vout goes down relative to Vn, it acts fine, but when Vout goes up relative to Vn, it actually turns on the junction here. And it means that at high temperature, the corner frequency is increased. So it means that at high temperature, the pixel won't see slowly moving edges. It'll basically filter them out, high pass filter them out. So at high temperature, it also increases the corner frequency. But I encourage you to look at this paper because there's more details disclosed there. There's been a remarkable advance in DBS readout speed over the last 20 years or so. When we started, we had address event word parallel readout as developed by Matt Civilotti and later Corbena Boahan. And the idea was that you had a pixel array. On each edge of the pixel array, you had an arbiter. This arbiter would arbitrate between the asynchronous row and column requests from the pixel array. And the way this would work is that a pixel would request in the row direction. It would get acknowledged in the row direction from the arbiter. Then you could send out the pixel a row number as an address. And then the active pixel would request in the column direction, acknowledge in the column direction, and now you could send out the pixel column address. And that actually is quite slow, but we could achieve at that time about 1 million events per second from a 128 by 128 array. Now, Quebena quickly increased the speed of this kind of readout and developed so-called AR word serial readout. And we implemented this on our first Davis sensor in 2014. Here, the pixel scheme is unchanged. You have an arbiter, same kind of arbiter, based on C elements and asynchronous arbiters developed by the asynchronous community to arbitrate between the rows of the sensor. But now the column is replaced by kind of a burst readout. So again, the pixel requests in the row direction is acknowledged in the row direction, but now all the active pixels in that row, now you can send out the row address, but now all the active pixels in that row can simultaneously request in the column direction, and now you can read out their column addresses quickly in burst mode. And so that increased the readout speed up to about 10 to 50 megavents per second, generally limited by USB now. Actually, at the sensor level, our sensor achieved 50 megavents per second. At the camera level, it goes down to about 10 megavents per second, limited basically by USB. And a key aspect of this kind of improved readout was that the event reset was decoupled from the arbitration. So once the pixel was acknowledged in the row direction, all these pixels make a request in the column direction, but then they start to reset themselves, independent of the communication of the events. This trend has continued now in industry developments, in particular from 2019 and 2020, with so-called group, vector, and frame-based readout. I'll just outline it, but you should look at these papers for the details. Again, you have an arbiter for the rows, same thing as before. So that selects a particular row with active pixel in it. So you can send out the row address, but now the column addresses are sent out in group or vector or frame-based mode, right? Where instead of sending out the individual address of each pixel, you send out words and you just mark the active pixels in these words. And that allows you to reduce the number of bits that you use per address by a large factor. And so here is a snapshot of the scheme from a Prophecy Sony paper from ISCAS last year. You can read about it there. But at the highest compression level of these so-called vectors, they get down to about 1.5 bits per active pixel. So this allows you to get really fast, up to a gigavent per second, or at least certainly hundreds of megavents per second by grouping the readout like this. And in fact, Samsung has pushed, and Samsung and Insightness are now pushing the idea, instead of reading out these event by event, you simply read out sparse frames of active pixels. For example, this is much better for interfacing to things like MIPI, Mobile Industry Processor Interface. It's just more compatible to be able to read out frames, sparse, highly compressed frames of events. And they can achieve nowadays easily kilo frame per second or 2 kilo frame per second in these senses of reading out these frames, these compressed frames of active pixels. I have to say, in relation to this DBS readout speed increase, this increasing readout speed somewhat goes against the notion of sparse output that the whole thing started with. Ideally, you shouldn't need these very high readout speed, but still it's good to have it, especially if your camera is moving, like in a driving or flying scenario. So I want to show you one example of a token ring group readout for DVS with the low power innovation DVS, as published in this paper, 132 by 104 10 micron pixel 250 microwatt 1 kilo event frame per second DVS with pixel parallel readout and spatial redundancy reduction. That's published in 2019 Symposium on VLSI Circuits. You can get it from the link here. But the idea of this thing was you have the array again, and along the edge you have circuits. Instead of being tree arbiters like they are in at least one of the dimensions of the current sensors, replace these AER tree arbiters by 1D token rings, which are commonly used in asynchronous logic design. And these token rings are clocked by the host receiver. at high frequency. And so one immediate advantage of this is that it removes the synchronizer delay, because now the host that's receiving the stuff, like a regular image sensor, is in command of the transaction and is simply scanning for data coming from the sensor. And so the pixels in this chip are built-in 65 nanometer, 1 poly, 9 metal, non-CMOS image sensor. So it's a prototype. They're 10 by 10 micron. They have a photodiode here. They have the circuits around in these 9 metal layers. You can see the dense layout here. And this chip has special feature of spatial temporal noise filtering. Like the Samsung DVS, there's some built-in noise filtering, which I won't talk about here. But the effect of these group of 4 pixels, as you see in here, is actually used in this group token ring group readout, as shown here. So here's one of these token rings here. There's a token, which is basically just a bit that passes through the token ring here. But when the column or the row of the array doesn't have any active pixels, the token just skips rapidly, very rapidly, like an inverter ring delay over those empty pixels. When it gets to the pixel that actually has data, which is actually a group of 2 by 2 pixels, it pauses for a moment so that this address can be sent out, and then it skips over the next non-active rows. And so this group of pixels, which handshakes with the array using a select and a request signal, then results in sending out a group address, which is an 8-bit address, and also the group events, also an 8-bit address, which represents the 2 by 2 pixels in this array. And so this is all under control of the host. And so the specifications of this sensor are shown here, this work. It's compared with a DVS from Samsung, this 640 by 480 DVS. So this sensor has much less pixels. The pixel size is a little bit bigger than the Samsung Pixel, even though it's built into finer process technology. But remember, this is a backside illuminated pixel. So this has a photodiode and some NMOS transistors on the back wafer. And so here it compares the array size. Actually, this sensor has pretty high readout speed, 180 mega events per second. And the readout efficiency in events per clock cycle, at best as 4 events per clock cycle, at worst as a quarter event per clock cycle, compared to the Samsung sensor, is better burst readout, higher burst readout using the group readout scheme, but the worst efficiency is much, much lower in the Samsung sensor. Okay, so it compares the power supply and the power. You shouldn't really compare it at the die level, but because the sensors are so different size. But the maximum power consumption of this Innovation DBS is about 5 milliwatts. At low event rate, it's only about 250 microwatt. But the way you really compare this is by pixel, per pixel energy. So the dynamic energy of sending out the events is 26 picojoules per sending out event. In this sensor, compared with, it's about a quarter of the Samsung level. And the static power, nanowatts per pixel, is some function of the biases, of course, but it's also smaller than the Samsung sensor. So as a result, this 132 by 100 DBS consumes about 500 microwatts at 200 kilo event per second readout speed. And so that makes it suitable for IoT applications. 500 microwatt, half a milliwatt at the chip level makes it so you could probably build a system that's probably a few milliwatts of static power consumption. And that puts it in the range of battery-powered IoT devices. Interesting sensor, so take a look at this paper about it. Now I'm going to tell you about building a complete USB event camera from a DVS or other kind of event camera chip. So one example of this, which I think is very beautiful, are a series of your Conrad's embedded DVS, which include a 32-bit fixed point microcontroller. And he keeps building more and more versions of these. This is from about 2007. And this embedded camera with all the computation sitting on the back here on this microcontroller was used to build this pencil balancing robot. You can see that this board with this embedded microcontroller is sitting here, and it's looking at the pencil from 2 complementary points of view. And so once you know from those 2 positions what's the angle of the pencil and the position of the pencil, you can use an algorithm, a beautiful continuous non-discretized Huff-based transform to extract the angle and position of the pencil from these two right angle views and develop a controller which runs on another 32-bit microcontroller here that controls this arm. And you can see that running here. This is actually me shooting the video with me in the field of view. There's the pencil. Here's Jörg Conrad and Timur Horiuchi. And this thing just is a lovely demonstration that demonstrates that you can update this estimate of the pencil at about 500 hertz doing all the visual computation on the 32-bit microcontroller that's wired straight to the AER bus on the DVS 128 chip. So read about that in this ICRA paper. But now I'm going to tell you about the development of USB interfaces. Now, every company that's now doing these cameras has some kind of interface to their DBS chip or their event camera chip. And they put a lot of work into it, many person years of work into this. You can read about our first developments here that Rafa Berner did as a master's project with the University of Sevilla, a 5 megavent per second, $100 USB 2.0 address event monitor sequencer interface. I encourage you to take a look at that paper, but in that paper it shows how to build the logic circuits to build a DBS camera like this, or actually this is a Davis camera. Here you see the physical camera. This is an early IndyLabs prototype, but you know, it's really about the size of a credit card, maybe, yeah, just about the size of a credit card. Here you can see the USB micro interface here, and the lens is clamped on top of the chip here with a simple lens holder. And this thing contains a lot of components. This is like years and years of development to get this all working. But here you can see the DBS chip, or the Davis chip actually. And over here, this orange block, which is this chip down here, is a USB chip. It's a Cypress FX3. It's kind of a configurable USB logic chip. And it also has pretty high speed, I think 200 or megahertz 32-bit microcontroller that mostly is used for housekeeping. It's the thing that talks by USB to the host computer. And it also attaches to an inertial measurement unit. This is like a $3 3 milliwatt sensor that's built into every smartphone that is like the vestibular system that we have in our ears. It measures camera rotation and camera acceleration through space, and it communicates with this microcontroller over SPI interface, serial peripheral interconnect interface. And then there's a big block in the middle. There's actually quite a lot of software on the CPU of the USB microcontroller. There are also the complex USB first in, first out memory buffers. There's at least 4 of them here that are taking the events from the FPGA that are coming from the Davis chip and buffering them in a round-robin fashion to optimize the transmission of the data to the host computer, because the host computer may not actually pull this bus that often, right? It gets busy doing other stuff. So these FIFOs are like capacitors for information. And setting up all this stuff here, again, takes like a year to figure out how to do all this complicated USB stuff with the enumeration and the different protocols. And now you have, you know, USB 3.0 super speed. When we started, it was USB 2.0 high speed, and then there's going to be, it keeps evolving. So you really need a lot of expertise, hands-on expertise to get this working. Now I'm going to tell you about this important block in the middle here, which is all the logic circuits that handshake with the chip and finally get the data from the chip in its various forms, intensity output, brightness change events, and so on, and buffer them together with possible external events like synchronizing events, pulses coming from another camera or computer or GPS time source, and multiplexes all this data together and sends it to the host computer. So the way this works is on your Davis chip, you have an address event interface, and in the case of our chip, it's an asynchronous interface. So it uses a 4-phase handshake with this word serial protocol that I just showed previously. But when the chip has an event to send, it raises request. The handshake state machine then raises acknowledge. The chip we read the address from the chip. Then the Davis chip lowers request, and the handshake machine lowers acknowledge. That's why it's called 4-phase, right? You go up one side, the other side, and then down, and then down, right? So up, up, down, down, like that. That's why it's 4-phase. Simplest possible handshake. But on the input to this handshake state machine, because this is asynchronous, you need a series of 2 deep flip-flops that are clocked by the system clock here to make sure that the logic system here doesn't go into metastability. So that's one interface. So this thing here, this handshake state machine, reads the addresses into this multiplexer here. This multiplexer then also takes the data from the camera's APS output. It's gray level frame output. Actually, this is our chips include a column parallel ADC, analog to digital converter, with a gray code output. It's just a parallel output of the digital values of the reset and signal levels. And this ADC state machine here manages the control of the shift registers, the multiplexers, and so on the chip, and then it reads the digital data for the frames in, and then it multiplexes it together with the asynchronous and bursty AER data, and together with the timestamps, because on this chip you also have to generate, on this FPGA, you also have to generate these microsecond timestamps and send them also to the host computer, so that your addresses or your brightness change events are timestamped. So all these things are multiplexed together, and these purple state machines here then all interact in order to orchestrate the data using different flags like write and FIFO full to get the data into a FIFO. So this is another memory FIFO that Rafa, I think, first implemented, and then Luca Longinati at InniLabs and then Innovation greatly improved on this whole framework. I'm sure other startups have done the same thing. But anyway, there's another set of FIFOs here that again buffer the information slightly to try to, because the data rate is variable, you want to minimize the chance that data is lost. Now you can always lose data because if the computer gets too busy here to service the data, these FIFOs can overflow. So you have to have a policy what you're going to do when the FIFOs overflow. Usually what we do is we discard the oldest data. We always make sure that we send the latest data. And then there's a complex FIFO state machine that then communicates between this FIFO and the USB FIFO using some flags. And there's another synchronizer state machine that takes, for example, the timestamp reset. So you may want to reset the timestamp to some value from the host computer. That comes over a control command from the host computer, and it results in setting this bit here, which goes to a pin on the FPGA, and it goes into the synchronizer state machine, which resets the timestamp counter, and it has to be synchronized together with other devices that might want to do this, and so on. So if you're interested in how all this works, take a look at Rafa's paper. It's quite easy to understand. And then there's a recent paper especially from Alejandro Linares Barranco's group at University of Sevilla, where it shows in general how to do this FPGA event processing, not just sending the data to the computer, but doing things like accumulating these events into frames and doing noise filtering and things like that. So check those papers out. Okay, what about using event cameras? I mean, if you want to actually explore these event cameras and use them, it's possible to do it now. It's not a hobbyist thing because R&D prototype DBS and Davis cameras, or whatever the manufacturer is calling them, are available from Innovation, Cygnus, Prophecy, Celipixel. You can buy prototypes from all these startups. They still cost a lot of money. For example, more than several $1,000s each. And they're mostly USB cameras. It makes it very convenient to work with them on PCs. There's no standard API like OpenCV for these event cameras. I'm just going to start the slides at a certain point. And also, I'll ask if there are any questions up to this point while I move to that part of the tutorial. You see there's a lot of technical detail, but I want to move to just applications now and show some of those things, if that's okay. So if there are any questions, it's a good time to ask right now. Does anybody have a question? Okay. Can they hear me now or not? Yeah, I think they can. Okay.
So Toby, there is one question in the chat, if you can take a look at it. It's
Yeah,
about the
the
cost.
question, yeah, okay, so the question is cost prevailing the penetration or wide adaptation? If yes, is there an opportunity for fellow research to work toward that direction? It's a good question. I'm not so closely involved with the startups. I think the companies are working really hard to try to land a mass production customer like driving or drone or security or consumer electronics like smartphone. But I think the main thing is cost. You know, people who buy these sensors, they're still buying pixels, right? And the pixels are still larger. So even though there's a lot of advantages in terms of information processing, reducing the amount of data and getting high dynamic range and good timing, you know, you're able to beat the power latency trade-off, but the pixels still cost more money. So you're getting like 4 times less pixels for the same money. And that's a big hurdle to get over. And as a result of that, you know, the take-up hasn't been that fast. We'll see what happens. Thanks for that question. I just want to talk a little bit about processing events. You know, I just want to finish with some actual applications. So I'm going to go to part 3 of the tutorial. I'm not sure if you can see the screen over here.
So Tobi, there are a few other questions. You can take them later on.
I'd like to answer the question. When designing the circuit, how a photoreceptor is modeled. Yeah, if you're interested in that, take a look at the V2E paper. And you'll see something about modeling the pixel behaviorally. And otherwise, you can just model the pixel in SPICE. You know, it's just this very simple CMOS circuit. You have to understand that the photocurrents are small and calculate realistic photocurrent values and realistic capacitance values for the photodiode. But it's quite easy to simulate the circuit in SPICE or behaviorally. There's another question is when designing this circuit, metaverse is buzzwords. I don't know about the metaverse. Don't ask me about that. You can ask Davide about that kind of stuff. Okay. So let me just show this part of the show. That's okay. Okay. Thank you. Okay. So let me turn now. I have to stop the share. I'm going to stop the share here and share with if possible, I'm going to try to share with sound. And optimize for a video clip. So it may be a little bit blurry. Intense section about DVS Pixel Circuit technology to algorithms and architectures for processing event camera output. And in particular, I want to talk about robotics applications, computer vision, and of course, deep learning applications of event cameras. So let's talk about representing and processing events. So how do you represent now when you're doing computer vision? How do you represent these DVS events? Well, it turns out that one very useful representation, particularly in the early days, was so-called image of most recent event timestamps, known variously as timestamp image, time surface, or surface of active events. This is the representation that we originally used in J way back around 2006. As soon as we had the camera, we started using this representation where instead of having a picture of intensities, you have a picture of the most recent event times. And then you can do operations on this picture which are driven by the events. So every time you get an event here, you write the time of the event into the pixel, and now you can do operations around that pixel that care about spatial temporal coherence of the events. For example, in detecting orientation. So for example, if you write the event time here, it's likely that if an edge is passing over the array, that the event times are going to be correlated. So you can detect the orientation of the edge by looking for the most coincident direction. So this is a widely used representation, especially in the neuromorphic community, because they like to think about using time and spatial temporal coherence of the events. Many algorithms use the timestamp image for exploiting fine event timing. For example, temporally coincident events that signal features or motion. I'll show you one way to do that, to exploit, without even using a time surface or timestamp image, how you can track objects from DVS events using spatial temporal coherence. This is an idea that dates back to the dawn of this DVS again. I'm going to now play you a recording that I made of data over Christmas in 2006 in Pasadena with our daughter Didi, who was only. So you might ask, how can you now count the number of cars that are passing by per unit time, measure how fast they're going, see whether they're changing lanes, and so on. Well, there's a simple algorithm which can track all these cars at very low CPU load, as you can see here. And the way this algorithm works is it exploits the fact that these cars emit these spike events like sparkler, the kind that you light at Christmas and wave around. And so now you can imagine tracking the cars just by forming a model of the car and then dragging the model along with the events. In particular, the steps of this algorithm are, for each event you get from the camera, find the nearest cluster. So suppose it's this one right here, you get a new event right here. If the event's within a cluster, like right here, then you move the cluster a little bit in the direction of the event. But if the event's not in the cluster like this one, you seed a new cluster, but you don't show it until it builds up enough support to say that it's a real car. And periodically, for example, every millisecond, you prune starved clusters, you merge clusters, etc., and you do so-called lifetime management. The beautiful thing about this algorithm is that it's very low computational cost, less than 5% of CPU load. You don't have any frame memory at all. You don't even use a timestamp image. The only memory you need is 100 bytes or so that you need to describe each object you're tracking, and you don't have any frame correspondence problem because there are no frames. So in between the traditional frames of computer vision, you just drag along these objects, event by event. And this allows you to do cool robotics things. The RoboGoalie is one demonstration of using a DVS here to solve a very quick, short latency visual control problem. And the idea is that a person here, in this case Florian, shoots balls at this goalie here, and the job of this robot is just to put the arm in the way of the ball. And the whole setup consists of a DVS, a servo, typical RC servo controlling the servo arm. And so you can imagine how you might solve this problem. If you know the position and velocity of the ball on the table, it's already constrained in 3D space. So it seems kind of simple to just put the arm in the way of the ball. You have to deal with calibration of the arm, and you have to do this really quickly. So this is a demonstration that was first developed at the Telluride Neuromorphic workshop around 2007. And I think it's a lovely demonstration of the advantage of the DBS. You can see the video here of this RoboGoalie running. You can see here how it can block the balls even though they're white or yellow on a kind of a yellowish table. Here you can see the paint stick arm and the servo and the prototype DVS. And now this shows here the view of these balls coming at the arm. So this is a top-down view from the Retina.
Now let's see some real action. Well, you have to be fair, you know. Hits you more than once.
So this algorithm allows you to track all these balls simultaneously and block the one that's most threatening. In other words, the one that's predicted to hit the Now, around 1988 to 2008, Jan LeCun and the team at Bell Labs developed the first convolutional neural networks. And you can see it here in this well-known video from Bell Labs, 1988-1993. Their first MNIST LeNet, the famous five-layer CNN. And this greatly inspired me when Jan came to visit us in Zurich. At that time, we were just developing the first DVS cameras, but it always stuck in the back of my mind, like to somehow combine DVS and CNN. So I'm going to show you now a demonstration of a CNN that is driven just like this small network here, but instead of by image frame, it's driven by DVS frames. So let me start by talking about activity-driven sampling strategies for exposing DVS frames. The first and simplest way is to use constant duration, like normal frame cameras, a constant time duration between each frame. It's simple, but it has no advantage over standard cameras except a high dynamic range. A second way that's widely used is constant count. You get the same number of events per frame. That means that the frame rate is actually variable and is determined by the motion in the scene. If there's no motion, there's no frames, and faster motion means higher frames per second. But a busy scene where large objects makes higher frame rate than a small object or a sparse scene, even if moving at the same speed, which can cause motion blur problems. Another way to expose such input to a deep neural network is to use interpolated voxel grid, popularized by Robotics Perception Group. The idea is that you generally use the same number of events per volume, but then you split this volume over a constant duration frames. So they call it voxel grid, but it's really just a certain number of frames where the event count is interpolated between the frames smoothly. It's a simple activity-driven way to create CNN input channels over time that preserves time dynamics across channels, but it has the same problems as constant count. Another way to do such things is so-called area count event, developed by myself and Min Liu in our work on optical flow with event cameras. The idea is very simple. The exposure of a frame ends when a sub-area fills with a certain number of events. So this is much better at resisting changes in scene size and so on. And it's a very simple and logic-friendly way to implement such an exposure policy.
I'm going to fast forward this.
Okay. Actually, in the last few years, there's been development. I'm now going to try to embed a so-called live demonstration of this rock, scissors, paper convolutional neural network that's driven by DVS. This cool thing about this demonstration, it illustrates the data-driven or activity-driven frames coming from DVS that drives an AI inference problem. And so you can guess what the problem's about. Basically, the computer always beats you at rock, scissors, paper. Let me ask you, how can a computer always guarantee to beat you at rock, scissors, paper? Very simple. It takes a long time, actually. People think about this rock, scissors, paper game as a guessing game, but if you could see me do this scissors or this paper or this rock in slow motion, then you could just react to that and do the thing to beat it. And so that's what we do. We just beat people in this demonstration by just using pure raw speed. And so now I'm going to include in this video here, I'm going to include a video of me doing this that I've recorded with screen capture because PowerPoint can't record the actual video. Okay, I've got here a Davis 346 camera, my office, mirroring the screen. Here I am. If I turn the frames on, we get the APS frames. If I turn them off, we just get the DVS output. I don't know if you can hear it here, but I can focus on a particular pixel so you can hear it. Or if I move the camera around, you can hear the typical kind of sparse firing pattern from such a pixel. Now what I'm going to demonstrate here is our Rochambeau CNN processing the output. So I'm going to choose, I'm going to enable this Rochambeau network, and now it's actually processing the output. Now if you see it here, it's detected my hand is showing rock, right? Instant I change scissors, it changed scissors, paper, paper. It's showing that the histogram here on the left is showing that the paper class is the one that's output. As soon as I go to rock or scissors, the beautiful thing about this CNN is that even if the scissors are very small or big, I can make them really big or small, or I can go to rock, make it small or huge, or paper, or I can take the other hand, paper, scissors, rock, here's rock. I mean, it's really lovely. It's just a lovely demonstration that Jan's CNNs really work here. You can see the null class, which is not anything. Right? The only problem is it detects my head as a rock usually. And you can see here how the output is processed in a data-driven way. If I am able to turn on the frames, I'm not sure if you're able to receive these frames, but I'm going to turn on now the actual input to the CNN. If I show the frames here, I'll attempt to put these on top of this recording so you see it at the same time. I'm not sure if this recording will be actually recorded, but the idea is here that each frame consists of 2,000 events. Right? So now there are new frames. Right? if I move my hand very, very slow, you see the discrete frames being recorded? But if I move it fast, the frames come much faster. So the beautiful thing about this is that no matter how fast I move my scissors, it's still sharp. But if I move it very slow, the CNN only does inference at very low frame rate. So this is constant count frames. But if I move it really fast, it doesn't get blurry. You can see the background video is actually still blurry. But because they're constant count frames, they don't get blurry.
Okay, for some reason the sound is not playing here. I don't know if you guys can hear me. This just summarizes that this sensor is a neuromorphic sensor that emulates key properties of the visual system. The wide dynamic range and the sparse quick output make this DVS useful for real-time uncontrolled conditions and allows beating this fundamental latency power trade-off. Especially the precise event timing could improve online learning and inference, as people in the computational neuroscience community like to think about spike-based learning rules. So that hasn't been explored that much. The applications of this kind of sensor technology include vision prosthetics, artificial eyes, Internet of Things, always-on surveillance, robotics, intelligent transportation systems, and human-computer interaction. Anytime you need to beat this latency power trade-off. The main challenge is to reduce the pixel size, that's an industry thing, and to develop effective algorithms. Industry can reduce pixel size, but it can't. But academia has plenty of room to play for the algorithms. And these event sensors, I think, including audio sensors, Shih-Chii is going to teach in her tutorial, can very nicely drive hardware AI. And they inspire hardware AI that exploits spatial and temporal sparsity, which I think is one of the key organizing principles of the brain that we can easily bring into digital technology. And I just want to stop and take some questions for the last 10 minutes of the session.
So it was very nice to see that you mentioned, that microsecond time resolution that is often quoted is a little bit false, and you showed a lot of these actual measurements. I had another question also, which was, we also see this noise coming up as jitter in the timestamps, right, for a certain stimulus. So to me, it seems like, what if I reduce the resolution of the timestamps? So for example, instead of microsecond, if I make it a millisecond timestamp, I'm in some sense increasing the quantization noise in time. And to me, it seems like it's optimal if I can make the time quantization to be similar to the noise-based quantization coming from the sensor. So instead of having a microsecond.
Well, you certainly won't lose much information if you do that, right? As long as your quantization is I suppose if your time quantization is still finer than the actual jitter, event timing jitter. And in fact, I think in the future, more and more of these kind of event sensors are going to be sort of semi-synchronous. People are going to choose some maximum sample rate, just like they do with frame-based cameras. They're going to choose that, and then everything's going to be quantized to that timing, and then it'll make the pixels smaller. In fact, you see that trend starting already, that some of that stuff that's inside the pixels, which is kind of expensive, gets moved out to the periphery. And then it helps to make, to help you just scan the array. And then you still get a very sparse output. You still get high dynamic range. You just lose this extremely fine time resolution of asynchronous circuits. So a little bit this field has been not bogged down, but it started from asynchronous circuit design. And it didn't take too much account of cost, silicon area cost. And of course, silicon area cost is very important, right, to get things to mass production. So that's why people are now moving stuff out to the edge of the array to get the pixels smaller and try to win the megapixel race, because it's clear that the industry is still mired. They wouldn't say mired, but occupied with the megapixel race, fully occupied, because they have to sell cameras with more pixels. Because for things like driving, you need lots of pixels. You don't have a moving eye. You need foveal resolution everywhere. Mm-hmm. And so you need little tiny pixels to see small objects far away.
Right. Okay, yeah, so there are a couple of more questions, I think. Yeah, thanks, Tobi.
Okay, so how does the power efficiency of the best circuit available compare with the human eye? And what numbers are we heading towards? Well, always lower is better. I mean, I can't be very specific, except that the human eye is really amazing. 3 milliwatts. Just think about what computation and what dynamic range and what complexity. I mean, I barely touched the complexity of computation of the human eye, which has these at least 20 different channels of processing. Like think like a 20 channel output CNN, where it's not just static frame output, right? These channels have lots of fancy dynamics in them. So we still have a long ways to go to match what the eye can do. And it's inspiring, but of course you have to sell stuff in the end. I hope that's helpful. And the second question is, does an ADC needed for integrating CNN to DVS sensor? Can regression also been performed live, only image classification tried? I'm not sure about that question exactly. In this Rochambeau demonstration that I showed you, I didn't explain how we trained the CNN. It's just a classic CNN that's driven by these DVS frames, trained in classic backpropagation by labeled data, where we labeled the data we collected a bunch of rock, scissors, and paper frames data from like 20 different people. Then we trained the little CNN, has 100,000 weights, takes about 20 mega-op per inference, and then we simply run it on the GPU. It takes about less than a millisecond to run on a GPU, laptop GPU, less than a millisecond. So it's a little tiny CNN. Of course, this CNN is doing very sparse operations because it's starting with extremely sparse input image. Only 5% of the pixels are active. The rest are just zero. So if you had an accelerator that can exploit that kind of activation sparsity, like a spiking neural network, or any sparsity exploiting activation, any accelerator that can exploit activation sparsity, you're going to have extreme sparsity in the network, and you're only going to be doing a few max out of all the max that are possible to do. So I'm convinced that's one of the futures of AI hardware accelerators that'll become more like these event cameras. They'll exploit activation sparsity. There's still a lot of stuff to do there.
Okay, yeah. Great. Thanks a lot, Tobi. I think.
By the way, I shared on the chat there the link. You'll see a Dropbox link to these slides. So anybody can just get the whole 2.5 gigabyte. It's a giant slide deck with all the videos. Anybody can just download that giant slide deck and look at it.
Perfect. Thank you so much.
Okay.
I think it'll be really useful for everybody in this session. Thanks a lot once again, Tobi, and
thank you. Thanks a lot, Arun. Good job.